So far, you've reduced the PageRank computation into one of linear algebra. Now in this lesson, we'll look at one more detail that you need to implement it, namely some options for storing the matrix, which will turn out to be sparse, meaning mostly zero. Let's get started. Remember the random surfer model? To each edge, we assigned a transition probability. That is, consider any edge connecting I to j. Then we assign that edge a value, pij. We say that this edge is weighted by that value. Now you can view the collection of weights as a matrix, capital P, whose ij entry is the weight of edge ij. Now look at the ith row of P. It only has non-zero entries wherever there are edges in the graph. Now in most real-world graphs, the number of non-zeros per row is relatively small, meaning that the matrix is mostly zero. So in those cases, we say that the graph or the matrix is sparse. So what's small? Well, sparsity doesn't have a precise definition, but as a rule of thumb, sparse means that the number of non-zeros in the matrix grows like the number of rows plus the number of columns. So by contrast, the number of non-zeros in a completely full or dense matrix would be the number of rows times the number of columns, which is big. Now, when the matrix is sparse, we can store it in a compact way. There are a bunch of options, but here are two common ones. The first is called coordinate or COO format. Now the idea is really simple. Let's store the matrix using three arrays or lists. One stores the row index of every non-zero. Let's call that capital I. Another stores the corresponding column indices. Let's call that capital J. And finally, the last list or array stores the values. So let's call that capital V. By this definition, each array has one entry for each non-zero. Let's number the positions by 0 through nnz, the number of non-zeros, minus 1. Now, suppose you want to multiply a vector by this matrix. So given two vectors, x and y, and a matrix A, compute y gets y plus a times x. In scalar form, for each element of the output, yi, you would compute a dot product between row I of matrix A and the vector x. So what does the code look like given a COO representation of A? Well, you could use a zipper iterator over capital I, capital J, and capital V. Now in this code, each non-zero value is little v, and its row and column indices are little I and little j. The code can then update each y sub I by little v times x sub j. Easy breezy. Now this format uses more storage than it needs. To see why, remember the picture of the sparse matrix and think about a row little I. All of its elements have the same row index, little I. So that means little I might appear several times in the row index array, capital I. Now this motivates a different storage format called compressed sparse row storage, or CSR for short. Now to see how it works, let's look at this matrix. It has n rows and 5 columns. Now like COO, CSR will use 3 arrays. The first is an array capital V, which stores the non-zeros. They're packed together row by row. The second is an array to hold the column indices. Let's call it capital J. Now it has the same size as capital V. The third array holds row pointers. Call it capital R. It's the size of the number of rows plus 1. For each row, it holds the starting index of that row in the V and J arrays. The last element is, therefore, the number of non-zeros. Now in this scheme, if nnz is much larger than n, then CSR saves about 1 array's worth of index metadata compared to COO. So what does sparse matrix vector multiply look like for a CSR matrix? Well, start by iterating over the row indices 0 through n-1 inclusive. Next, iterate over the positions in capital V and capital J corresponding to row I. So let's call each position K. Then the code can update Y sub I by the product of big V sub K and X sub J sub K. Then the code can update Y sub I by the product big V sub K and X sub J sub K. Got it? So with that discussion of data structures for sparse matrices, you now have all the pieces you need to implement PageRank. So we've prepared a Jupyter notebook for you that asks you to apply a PageRank style algorithm to a real graph, which is one that represents the airline network in the United States. I think you'll find it to be a fun exercise. All right, so good luck and see you again soon.